Pre-packaged statistical tools handle the heavy lifting of regression in the background. Building models in Python requires a rigorous, explicit architecture where we import libraries, define matrices, and structure every estimation step manually. We will apply this approach to the ISLR credit dataset. This data tracks continuous financial metrics like income and credit limits, alongside categorical variables like gender and student status. Our primary objective is to use these specific variables to accurately forecast average credit card balances. Before executing any regression equations, we must first mathematically define our standard of estimation and confidence. We need a quantitative method to measure our own uncertainty. Robust financial econometrics begins with manually constructing the boundaries of our uncertainty, rather than fitting lines to a scatterplot without a diagnostic framework. Traditional asymptotic theory relies on strict normality assumptions. It expects the data to follow a perfect symmetrical bell curve, a condition that real-world financial data rarely meets. To bypass this limitation, we use the Monte Carlo bootstrap. Bootstrapping is a programmatic solution involving the resampling of our observed data with replacement thousands of times to estimate the distribution of a statistic. This iterative resampling approximates the true sampling distribution. It builds a complete map of our estimator based solely on the observed data, eliminating the need for theoretical assumptions. This histogram shows the bootstrap distribution of sample means created through our Python loop. We extract the 95% confidence intervals by manually defining boundaries at the 2.5% and 97.5 percentiles. The vertical blue lines mark exactly where these bounds fall. Bootstrapping provides an assumption-free foundation. However, establishing confidence bounds is only the first step in diagnosing a model's true predictive power. Let's propose a baseline, single-variable model where we predict a user's average credit card balance using only their credit limit. This scatter plot shows our simple, ordinary least squares, or OLS, regression. The red line represents the model's trajectory through the data points. The summary yields an R-squared of 0.74, a metric representing the proportion of variance in the dependent variable predictable from the independent variable. R-squared is merely a summary statistic. It is susceptible to hiding structural flaws, such as nonlinear patterns or severe anomalies in the dataset. A high R-squared value is deceptive if the underlying covariance matrix is compromised. We must interrogate the residuals. A residual is the exact difference between an observed data point and the model's predicted value. Data scientists analyze 3 tiers of residuals: raw, internally standardized, and externally studentized. Internal standardization suffers from the masking effect. When calculating the error, a massive outlier pulls the regression line toward itself. As the line moves closer, the overall standard error band inflates. Because the outlier inflated the total standard error, its own distance from the line appears normal. The outlier successfully disguises its own anomaly. The solution is the externally studentized residual. This algorithm refits the regression model from scratch, while leaving out the observation in question, yielding a metric that reveals how unusual that specific point truly is. These diagnostic plots reveal the true variance of the dataset. In the middle panel, studentized residuals versus fitted values, the dashed orange lines represent plus or minus 3 standard deviations. We flag any point beyond these boundaries as a structural deviation. By unmasking the data's true shape, we can safely project our model into higher dimensions. When adding multiple variables like income and gender, the geometry of our prediction shifts from a 2-dimensional line to a multidimensional plane. A standard multiple regression without interactions assumes parallel slopes. The model expects the effect of income to remain identical for both men and women, differing only by a fixed baseline intercept. We introduce an interaction term to test if those variable slopes diverge. An interaction term multiplies 2 variables together to measure if the effect of one predictor depends on the level of the other. This nested F-test creates a visible geometric shift. On the left, the non-interacting model forms a flat plane. On the right, the interacting model creates a twisted manifold, adapting based on rating. If significant, we retain main effects, even if isolated t-tests fail. Regression is the deliberate sculpting of a multidimensional prediction space. Adding or dropping variables without a clear strategy introduces severe bias. In 1973, the University of California, Berkeley faced a famous case where overall graduate admission rates appeared biased against women, yet department-level data showed the exact opposite. This is Simpson's paradox. It occurs when omitting a critical covariate entirely reverses the magnitude and polarity of a coefficient. In our credit dataset, the coefficient for student status changes based on the formula. If we omit income, being a student appears to increase credit balances. If we include income, the magnitude and direction of that effect shifts. Including too many variables introduces multicollinearity. This scatterplot matrix displays the pairwise relationships between all continuous variables in our dataset. The intersection of limit and rating shows a near-perfect correlation of 0.997. The regression cannot distinguish the effect of a credit limit from a credit rating because they move in exact tandem. We detect this instability using variance inflation factors, or VIF. A variance inflation factor is a measure that quantifies how much the variance of an estimated regression coefficient increases because of collinearity. A score over 5 makes our standard errors unreliable. Navigating between omitted variable bias and multicollinearity requires an algorithmic method of variable selection. Stepwise regression is a programmatic screening tool. It adds or removes variables from the model based on whether their individual p-values cross a 0.05 threshold. Stepwise is a greedy algorithm. It locks in early choices based on local improvements and often misses the true global optimum of the dataset. Best subset selection is the definitive mathematical solution. It requires the computational evaluation of every possible variable combination, represented as C and K. We cannot use standard R-squared to judge these subsets. R-squared artificially increases with every variable added, rewarding overly complex models. We use penalized criteria like adjusted R-squared, AIC, Schwartz BIC, and Mallows CP. Information criteria like AIC and BIC are metrics that penalize the likelihood of a model based on the number of parameters to prevent overfitting. Mallows CP is a technique that assesses the fit of a regression model while accounting for the potential bias introduced by including too few variables. The final output of our Python subset loop reveals the optimal model. By evaluating all criteria simultaneously, the algorithm balances predictive power and parsimony by isolating exactly 2 variables, rating and income. The optimal OLS model survives rigorous diagnostic unmasking and algorithmic subset selection, prioritizing mathematical stability over a high raw fit.